Hello, everyone, and welcome to the Quantum Machine Learning track. In this session, we will continue building our foundation in data science and machine learning. This is our second session in machine learning track, where we will further revision our understanding of data science and machine learning concepts with the engineering sum up. If you have any questions during the session, please feel free to raise hand. We will be happy to answer them. We encourage you to actively participate and take full advantage of this opportunity. Let's get started.
Hello and welcome back to our sessions. Let's break the ice between us again and tell me, how was the assignment with you? Was it hard, bad, good? I want to know your review. Go on, Ala.
Yeah, I guess the BCA part and the engineering part had some problems.
Uh-huh.
I asked for an extended day because I didn't take the data science before, so I'm just finding out, figuring it out with myself.
Yeah, I know this will be a bit hard in finding out with yourself the resources, but for the resources, it will be so easy to write a PCA analysis on Google, and I think Geek for Geeks have a very good overview about it and a sample of the code that you can use. But the idea here is how to use it. It's not about the idea or the concept of the PCA, but it is about how can you implement this code on any other notebooks. So feel free to ask me any time about it. And for today, if you didn't find a resource or something till tomorrow, you can send to me on the classroom, and I will be happy to provide a full detailed code for the PCA, but it will be a general code. You will have to customize it according to your notebook. And the idea of the assignment with me was about you knowing something and you don't know the other part, so you have to search and know how it will work. And the concept of data science is not that hard. It is about the way of thinking, your way of thinking, about how you can actively do something on the notebook that will affect positive in a positive manner on it. So anyone else, what do you think about the assignment? I'd like to hear you, so go on. Okay. And again, feel free to ask anything to me directly or on the classroom, and I will be happy to share anything with you, resources, code, and so on. And I will grade the assignments as soon as the deadline finishes. Okay.
Yeah, thank you so much.
You're welcome. Okay, so let's go to our session today. Our session today won't be long, but it will have too much details, or you can say as much details as needed. It will be about 3 parts. Let's go to the objective of this session and what you will be able to do after finishing it. So, in this session, by the end of it, you can understand the supervised learning workflow for data to production, differentiate between classification and regression problems, explain 3 main models that we will be working on throughout this lab or this course, Quantum Lab, which is logistic regression, SVM, and neural networks. Describe how training and optimization happens. So let's agree that description here, I will explain in detail how it will be going on, but I won't provide a full code for it. And feel free to ask about the code at the end of the session. We will compare the models, and the idea here, I want us to agree on it. it's not about knowing the parameters and how the parameters of the model. It is very important, and it is very important to know how or when to use the model with which problem. And this is my objective from this session. I need you to fully understand, if I see this problem, so I will go to that model. If I see this problem, so I'll go to that model. So logistic regression and SVM are just two models from a million models that we can use. We have other models, so feel free to search about it, which is random forest and so on. So let's begin. The first question I want to ask is, what do you know about machine learning? If anyone see something or know something, please raise your hand and share it with me. And if you have no experience at all, please make a thumbs up or raise your hand. Marwan, go on.
Okay, machine learning is a way of inferential statistics where we have data and then we train a model based on the probabilistic distributions within these data. We can infer about a specific target variable, either in as you have said, in a regression where it predicts a continuous value or a specific loss in a classification problem.
Yeah.
There are different models within the machine learning. Deep learning is a part of the machine learning itself, but in a very broad, general manner, it's basically inferential statistics.
Okay, perfect. That is a very fine answer. Anyone else would like to participate? Okay, so let's go on. In general, machine learning is about the learning of a model. So he can predict something he knows or he don't know. And this will be according to our problem. Some problems, the data will have the answer inside of it. So we give the model the data with the answers. And then he trains on it and knows the answer and knows the data well. Then we experience it or test it on unseen data or a hidden data or a data he don't know. So we can know how did the model act according to something he didn't see. And we have another type of a problem where we don't know where is the problem or where is the answer. So the model must predict or detect the patterns inside the data and knows the answer. So in general, machine learning is about learning from specific data to do a prediction or to have an answer to a question that we know or that we don't know. We have many types inside the machine learning. First of all, we have the supervised machine learning. And this is what Marwan was talking about, that we have data and we have its answers. So we feed the model and train it on the data and the answers. After finishing all of this, we tested the data or we tested the model on unseen data he didn't see before, to predict the answers from the patterns that he learned from the training. Then we have the second type, which is unsupervised. The unsupervised, we can say it's the sneaky one. The data don't have its answers. We don't know the answers of the specific row or the answer of the specific data. So the model must know the hidden patterns, the structures, the relationships, what is anomaly, what is unordinary in this data, and he is trying to discover the answer of this data. We have the third type, which is the reinforcement learning. Reinforcement learning is like trial and error. If the model do something right, so we give him a reward, and he will continue as it is. But if he answers wrong, we get him an error or a penalty and say that's wrong, and he will stop it and begin again from the beginning to the point that we stopped at, and he will try again till he figures out the maximum reward size in this environment or in this game. Then fourth, we have the deep learning. The deep learning here is about artificial neural networks, and let's not talk about it now. We will talk about it later today. Afterwards, let's dive deeper inside the supervised learning algorithms. Here, this is my focus in this session. Supervised learning algorithm, it is about a data. The data have its answers. So the model maps the inputs to the outputs. And maps here means he knows the pattern of the data that I have that reaches this specific answer. Then it widely trains and classifies the data. We have three main things inside supervised learning algorithm. We have the regression problem. The regression problem is predicting the continuous values, which is the house prices, stock prices, including linear regression and SVMs. Classification. We are classifying the problem, dogs, cats, tall, short, and meds, which is not tall and not short. Then we are classifying red, green, yellow. So the classification, it is about grouping the things that have the same answer or have the same pattern or have the same properties. So here identifying if the spam is email or not. Diagnosing diseases, knowing that if this disease occurs in this sample or not. This includes decision trees and logistic regression. Then we have the ensemble method. The ensemble method here means combining multiple algorithms with each other. Sometimes the problem is very hard, or it's not very hard, it is complex, that one model will not drive us to the point that we want. So we do combine multiple algorithms to improve the accuracy, to improve the robustness. The example here means random first. Random first, it is the same as decision tree, but it is many decision trees with each other, with each other, and the gradient boosting machines. So, is there any question here or anything that is uncommon? Okay. Then let's have a quick overview about unsupervised learning algorithm. The unsupervised learning algorithm that we have a data, but we don't have its solution. We don't know the answer. So the training model or the model must know the hidden patterns, the structures of the data, and often the data, it is meant for exploration, dimensionality reduction, or anomaly detection, knowing that this is normal, but there is unusual behavior here. So we will penalize this or say this is something abnormal. We have three things in it. Clustering. Clustering means grouping the points of data on their similarities, as k-means, or hierarchical clustering. Dimensionality reductions, and we have talked about this in the last session. It is about the high dimensional data. The high dimensional data comes from how many features do we have here. As many features as we have, as many dimensions as we have. By reducing the number of the features, by preserving the essential information. We must preserve the information that we have without losing additional information, but also we have to reduce the dimensionality of this data. Examples here like PCA or Tessany or something like this, and Tessany is another way for dimensionality reduction. Feel free to search about it. Then we have the association rule learning, which is discovering the relationships between the items in the dataset. As we have agreed before that unsupervised learning have a hidden patterns. We must discover the relationships between the data. So we use association rule learning. And then we will have from unsupervised learning model to the selection. So let's dive deeper in the supervised learning that we will need to know this session. So is there any questions till now? Okay, let's continue. My goal here is to know what is the right model for the right problem. To solve the supervised model, Minna, go on. Minna? Minna, can you hear me? Okay, let's continue till Minna. Yeah, Minna?
Thank you so much. Can you hear me?
I can't hear you at all. Your voice is so low.
Can you hear me? I have a connection issue. The screen is freezing.
Again. Say what you have said again. Say what you have said again.
If you hear me, I was asking about the dimensionality reduction.
Yeah.
Dealing with feature like feature selection and feature extraction. Like I'm reducing the n of features or n of attributes I have in my data, for instance. So I'm dealing here with another part, regardless to the machine learning or the algorithms, like PCA or
the PCA, yeah, regardless.
So why it's involved into the machine learning or the unsupervised types? Isn't it should be with dealing with features or attributes? Thanks.
You were asking about why PCA is involved, right? I hope I could hear you, I could have heard you right. Why PCA is involved in the unsupervised as something or as a problem, right? Look, in supervised learning, we have said that the data have its inputs. So PCA here can be a crucial thing if you have a high dimensionality or high number of features. But PCA here is considered as an unsupervised because PCA does not use labels. Labels here, I mean no target value. There is no answer for the data. So we considered it as an unsupervised method. So when I look at X of feature or N of attributes or so on, we don't have a target variable. We don't have a no class information, no supervision. So what PCA actually does, he tries to find the new directions in the data to capture the maximum variance. So it asks what is the data spread most? What is the direction of the most structure? We don't ask about the class label. We don't ask about the predicting. So this is why it is supervised. But again, it does not mean it is not used in general to make the dimensionality reduced. Okay, for supervised learning, we have an X features and X labels mapping from X to Y using logistic regression, SVM, or neural network. But inside an unsupervised learning, we have X only. X only here discovers the structure in the data. Example, like PCA, key means, and hierarchical clustering. So PCA is grouped with unsupervised learning, but it doesn't mean that we don't use it for dimensionality reduction. Okay. Okay, let's continue. Here, the goal inside the supervised learning model or the selection of the model is to know the mathematical function or the mathematical algorithms that the model use, the loss function, the optimization method, or how to optimize the accuracy or the training of this model, and a way to evaluate the performance. Let's, here in the evaluating of performance, we have different ways of evaluation. And according to the problem, we use this evaluation performance as squared error or RMSE or MSE only, or discovering the accuracy and so on. So according to the problem, we find its evaluation performance. In this session, we will focus on logistic regression, SVM, neural network, how each model learns, how to optimize each model, and the performance depending on the data, and take care that choosing the model is depending on the data. And the second thing, that you don't have to know all of the parameters of the model, but you have to know how the model works, how to optimize it, and how to use it. So when you use it in a problem, you don't have any problem for thinking or know how it works. So let's dive deeper inside the supervised learning workflow. First of all, we have to define the problem, either classification or a regression. Then prepare the data using the methods that we have taken the last session, or other methods that will enhance your data preparation. Third thing is split the data into training and test method. Why do we do the splitting? For our data, it is very bad for the model to have the whole data set in the training and then testing the whole data inside the testing. It will have a very high accuracy since he have seen these patterns before, so it will be easy on him. So we split the data into 80% of training and 20% of testing, or 50% of training and 50% of testing. And we have a third split, which is the validation. The validation here, it is about validating the data, but it won't be used today. Choose the model. We choose the model according to the problem that we have. Then, after choosing the model, training it. Most of the time, the first training won't be the highest accuracy or the best one, so we will try to optimize the loss. Our goal is always to have the minimum loss inside the model. The minimum, the loss that you have, the better the model that acts. Then evaluate the model, and the evaluation here happens inside the test. We test it and evaluate the model. Then we can again improve and tune the model and evaluate it again. And this is a simple process of supervised learning. So is there any question till now? So we will begin on our model, our first model. Okay, let's go. Our first model that we will be talking about is logistic regression. So I'd like to ask you, what do you know about logistic regression if you hear about it? Go on, Marwan.
It's a model that's used to choose between two classes, and
Okay.
it predicts the percentage or the probability of the input data that it has taken belongs to the positive class. For example, it took an input X, it will predict if it's 80% its output, then it's 80% belonging to the positive class.
Okay, perfect. Thank you. Does anyone have any other opinion about logistic regression? Go on, Manna.
Okay, as my knowledge, logistic regression, I think, is the same as regression, but it's for classification problem, as it's has the same regression name and also the logic. I'm going to split my data into classes, so I use a line or a linear line, which is linear in its detail, as it have the equation of the straight line. And the logistics indicates to the logarithm or the logistics function. It acts like threshold, which this line, maybe the value or the result of this line will put into the or fit into the logistic function, which acts like threshold to define which class it's belong to.
Yeah, I
I'm
think
trying to make
yeah,
relation
this is
between the
perfect.
name. Thanks. I'm trying to
Continue.
make a relation between the name and the model or the topic we are dealing with.
Okay, that was more than perfect. So what is a logistic regression? The logistic regression that we are talking about here is about a supervised learning algorithm which is used for classification problems. Unlike the linear regression, it was used to predict the values and that is the probability on which input belongs to a specific. Okay. So is it the same as linear regression? Yeah, you can say that it have the same equation, but it is not the same usage. So logistic regression predicts the probability of the binary outcome. Is it yes or no? Is it 0 or 1? We use something called sigmoid function, and so the sigmoid function here is used to map the input probabilities that we have. Either for classification, so we enter the input features, then the linear combination, then by the sigmoid function we determines where are we. And again, so to make it clear, linear regression is used to predict continuous values, uses best fit line, solve regression problems. But for logistic regression, it predicts a categorical class, uses something called segmented in detail, and solves the classification problem. Is there any questions still now about the what is logistic regression? So let's continue. And this is what I have said, logistic regression is a supervised classification about the output. Can be possible categories of yes or no, true or false, 0 or 1. It uses the sigmoid function to convert the inputs into the probability. So let's continue. Here, the intuition behind the logistic regression. I have said something earlier that what I do here is I took the input features, then I do a linear combination, then I feed it inside the sigmoid parameters. So this means that it uses the same equations that our linear regression uses, which is z equal w1x1 plus w2x2 plus w3xb till we finishes our feature plus b. And let's say what is this? Z is the output feature, x1, x2, x2, x3, x4, which is our features or our attributes or our data. W1, W2, W3, and so on, which is the weights. How important is this feature to us inside our data? And we have the B, which is called the bias. After finishing these two steps, or this one step, we apply a nonlinear transformation, which is the sigmoid functions. It creates a decision boundary. If the relationship is linearly separable, it works very well. But if it's not linearly separable, it is a non-linear transformation, and we have to use sigmoid functions. Again, the intuition behind the logistic regression have, we can say, 5 attributes, which is the most important one. The independent variable. Each point inside our data at the very beginning, it is independent. It does not relate to anything. No correlation. It has no relation between any other points or between the input samples and each other. Then we have the binary dependent variables. So the assumption here is that the dependent variable must be binary, means that it only takes two variables. And for more than two categories, we use something called soft max. But we won't be diving deeper inside having more than two categories. Then we try to figure out the linear relation between the independent variable and the log odds or the binary dependent variable. The model assumes that there is a linear relation between the independent variable and the dependent variables. Then, by prediction and so on, we will see how it is linear or how it's non-linear. Then, and this is the most important thing, data must have no outliers. The data should not contain any extreme outlier because this model is very sensitive to outliers, very, very sensitive to outliers. And it can distort the estimation of the logistic regression coefficients. And the large sample size. It requires a sufficiently large sample data to be reliable and stable, and take care of the last two things. Is there any question until now? Okay, perfect. Now we will go to the main start of the logistic regression, which is the sigmoid function. After feeding our data to the model, see the linear relations between it with the linear regression equation, which is z equal or z equal or y equal w1 x1 and so on. We fed it inside the sigmoid function. The sigmoid function is the important part of the logistic regression. It used to convert the raw output of the model into a probability of 0 and 1. And this is why we use logistic regression. We can say it is like normalizing the data between the values 0 and 1. The function here takes any real number and maps it inside of it. So what is our equation? Our equation is here, which is y equal, here, if you can see it, y equal 1 over 1 plus e power minus z. And this is the main equation that the sigmoid function depends on it. So when the output of the model comes, it fed inside the sigmoid function to convert the output to fit inside the values of zeros and 1. And it will be a real numbers. And the maps it inside the escape forming an escape, an S-shaped curve. The S-shaped curve have a threshold. The threshold here usually 0.5. What is below 0.5 will be 0. What is above 0.5 will be 1. So I want to ask a question here. For any problem, the threshold that I have is always 0.5, or it depends on the problem? Tell me, what do you think? Marcel, go on.
For using the sigmoid function, it ranges between 0 to 1, so it's obviously that it should be 0.5. But for different problems, the threshold ranged for different numbers.
Okay. Minna?
That's all my comments. I'm adding to Marcel's comments. 0.5 is the midpoint between the classes, so I have to choose the midpoint, which according to it, I'm going to classify or categorize my classes. So
But
it's either maybe less than 0.5 or more than 0.5. So according to it, I will get the value for it 1 or 0.
Okay. Yes. This is nice, but take care of something. Sometimes we have something called a class imbalance. Class imbalance means that sometimes the data is not separated correctly. We have 70% of yes and 20% of no. So now the threshold at 0.5, it will be that the most of the data will be yes, so it can have an overfitting. So the threshold again is usually 0.5, but it can be lower or higher according to our problem. And take care of the class imbalance thing, because it will make the data more complex, or it will have, you have to solve the data. So here, specifically inside the linear or the logistic regression, since the class imbalance will literally affect the data so much, or affect the model output so much. So you must have a data that have a 50% of yes and a 50% of no to have a threshold at 0.5. But in other cases, sometimes we want to have the threshold at 0.5. It can be higher or lower according to your problem and according to the data that you have. So if and again, if the threshold varies, it can be 0.7 and so on. So what is below 0.7 will be 0, and what is above 0.7 will be 1. So if the threshold is 0.3, then what is below 0.3 will be 0, and what is above 0.3 will be 1. But this is according to our problem. So how do we know this? This thing, we know it when we train the model and find that the accuracy is so bad. So the first thing we are trying to do is playing with the threshold that we have. So it is not necessary to have a threshold at 0.5. Okay. The input, again, this is a brief explanation of what I have said now. And let's go to our loss function. We have said that the logistic regression depends on a probability. And the probability here affects our loss function. And our goal is always to have the minimum loss function that we have. Okay. So the question here, how do I know the loss function? Or what is the math behind the loss function? So let's continue here. The loss function inside the logistic regression is binary cross entropy. Entropy means how much information does this system or does this model gain. So this is a very important thing. So the entropy is the knowledge that we gained. The loss function is the knowledge that we have not gained. So we must make it as minimum as possible. Inside the linear regression, we use the mean square error to know the evaluation or know the performance. But inside the logistic regression, we use the loss function. This is the equation of the loss function, and it depends on what? It depends on the dependent variable that depends on our feature and the probability that we have from our sigmoid function. Cross entropy works better for probability outputs. So this is why we are not using mean square error. Mean square error is used usually for regression problems. Transforming a linear regression, this is how it works. We transform the linear regression from a continuous value output into a categorical value output using the sigmoid function, which is mapping the real values and so on. But as shown here, we know how it is converted. We have sigma of z. Sigma here, it is from the problem or from the sigmoid function, tends towards 1, so means that the z tends to infinity. But if it tends towards 0, means that the z or the function or the target value that we are, the dependent variable that we are trying to guess, it is towards negative minus infinity. So again, sigma z, which is the output of our sigmoid function, it is always bounded between 0 and 1. Where the probability is being usually as, if the probability is equal once, then it is sigmoid z. But if the probability tends to 0, then it is 1 minus sigmoid z. Okay, is this clear till now? Okay, then we will have something called the gradient descent. the gradient descent is one of the most important things that we care about. The gradient descent is about finding the global minimum point inside our problem. So I want to ask you a question. Most of the problems that we have only one global minimum or have more than one point of minimum value? Go on, Marwan.
It will have a single global minimum because the chosen loss function is convex.
Okay, that is very nice. Yes, and also this depends on someone raised his hand, so go on.
No, it was by mistake. I'm sorry.
Okay. So here the gradient descent, how it works. We have said that the equation is what is z equal w1x1 w plus w2x2 plus w3x3 according to our number of features plus something called of the bias. So how does the training process works? It works with the gradient descent. The gradient descent is you can say it is parabola shaped or an inverse bell shaped. You can put the bell shape in upside down, and you will have the gradient descent. First of all, the weight is initialized randomly, so we don't know which feature affects the data most. So we initialize the weight randomly, then we compute our prediction. Then we compute our loss. So if we find our loss is very high, we must see what happens to the weight. So we come again and compute the gradient, update the weight, and this is how we update our weight, which is the weight that we have, the new weight, W new equal W old minus the learning rate that we have. And the learning rate is one of the most important things that we have. If the learning weight is very high, we have the learning weight L1. So if the learning weight rate is very, very high, the model will become unstable. Unstable means that the predictions won't be that stable or that good, multiplied by gradient. So the most affected learning rate, it is the low learning rates, which is 0.1 most probably, or 0.3 and so on. So we have a slow learning rate, will be stable, and the model will become robustness, and it won't affect by anything that we have. And we will repeat until convergence. And the link here that I have provided will talk more about the data, the learning parameters that we have. So let's go on to the next slide and see. Go on, Alan.
I got a question here, and if the learning rate is high, is that related to actually cause like a data leaking or something like this, or this
Yes.
is another?
Yes. High learning rate means that the model is unstable, means that the model is learning so fast. So it makes us a data leakage, a problem in the model which will be unstable, and it will have so many problems. So yes, having a very high learning rate won't be good. And here I have provided a link. What does this link do? Let's see. This link is about the parameters of our parameters inside of the scikit-learn or the logistic regression. Let's see. I will share my screen now. And again, I want to tell you that you don't have to know all of the parameters inside the logistic regression to use it, but you have to know the main parameters inside the logistic regression. So you will be able to perform the tasks that you want, and if anything happens or anything that you don't know, you can always return to the documents, which is the documents of the logistic regression, to know the parameters that you will need by default. Okay, give me a second. And here is our document of the logistic regression. So tell me if you can see the screen now. You can stop all of the sharings and share my screen again. Yeah, it was freezing. I don't know why. So till the finishes loading, let's see, because I have something in internet. I don't know why. Okay. So let's continue, and I will show you the parameters in detail of the logistic regression. Now you can see my screen. Before the lab, I will show you the parameters that I want to show you. Then, for the optimization inside the logistic regression, we have three main types inside of it. So you can read it for a second and tell me what do you understand from it. So what do you think about the three ways that we have to enhance it or optimize the logistic regression? Okay, go on.
You have said that we update the weights, so batch gradient is send the updated weight, and
Yeah.
with every update, it updates the entire data set, so it makes it slower. It costs resources and time. For the stochastic gradient descent, it updates per the sample. We take a sample, so it's more faster than updating the entire data set each time. For the mini batch, I guess we take a group of samples and we work on it. I'm not sure.
Yeah, that's perfect. That's nice. Yes, you said it in a good way. So, does anyone? Yeah, go on.
Yeah, I think also, as my friend said, stochastic is important here for the benefits that leads to an increased rate of conversions, because that's the point of the sequence of the process.
Okay, that's nice too. Our goal is to make the model performs at the best inside the training model, so we can have the best evaluation thing. And for updating the weights, we have many different types. We have, I don't know what have happened, but okay. we have the mini patch learning. Patch learning here, I mean that I take patch of the data, update its weight, and try it. From it, I determine the loss function here and the loss function in this patch and the loss function in this patch. So it won't cost a lot and it will see all of the data. We have the normal gradient descent. So can you hear me? Is my voice clear? Can you hear me?
Yes, we hear you.
Yeah, okay. For the normal gradient descent, it takes the whole data, update the whole weight of the data, and then what? And then it takes the loss function inside all of this data. So sometimes yeah, go on. Ahmed, go on.
Okay, I just have a question about the loss function.
Yeah, for sure. Go on.
Why is it defined in such a way? Yani, what is y in the loss function?
The loss function here depends on what? Depends on our output, depends on the probability that the model will have. So the loss function, we must minimize it as possible. So from this equation, let's go back. From this equation, we will try to have the minimum loss function that we could have. So we depends
But
on
why?
the depend. But
What is
why?
y here?
So
What is y here?
Y here means the output or the dependent. We have said that the equation is z equal x1 plus x2, x1 w1 plus x2 w2, and z can be y. Y equal x1 w1 plus x2 w2. So y here is the dependent variable.
Is the output of the decision?
It is the output of the decision, and this is the probability of the decision.
Okay.
Okay.
It's fine.
So we have the patch gradient descent, which is we uses the entire dataset in each update. It is stable, but it is slow for large data. So if you are training a very large data, it will be very slow. Then we have this stochastic gradient descent, which is update per sample. It is faster, but noisier updates, where if we have an outlier, if we have a noise inside the data, it will affect it. It will be very affected inside our loss function. The minimum patch, the patch gradient descent, this used in practice, which is the best balance. We took a number of samples, update its weight and determines its loss, then go to another patch, do its weight and determines its loss, and so on. And each one of it is used for a specific type of data and according to our problem again. So before going to a lab, I will share with you the logistic regression parameters. Here, this is our logistic regression parameters. Okay. This is the official documentation of logistic regression. And the point here is it's not about, again, knowing all the parameters. The point for me is to know how to use each parameter in what way. So logistic regression is used here from sklearn.model.logistic regression. We have here the penalty. The penalty means the specific random norm of a penalty. Penalty, which is an error or something like this. So we have L1, L2, L-stanip, and so on. So you have to take care about it, and we want to use it until doing an enhancement or so on. The class weight. The class weight here, I have defined before, or I have said before, that sometimes, not all of the time, the data can have a class imbalance. The class imbalance here means that the data is not distributed correctly. What I mean that the yes is bigger, the class yes is bigger than the class no, or the class no is bigger than yes, and so on. And this is what I mean in class imbalance. So the logistic regression have something called the class weight. We said here, if we can enter a dictionary if the class is not balanced. So I can enter how is the balance working inside this data, if it's balanced, or none, which is mean balanced. Weight are associated with each class. Okay, So take care, this is the way that the gradient descent uses to make its thing. Then we have a random state. The random state, it is an instant for shuffling. Okay, it is used for shuffle the data. We have the solver. The solver, it is the algorithm used to optimize the problem or used for the problem. We have LBFJs, and this is all an algorithms that is used inside of it. Linear, Newton CG, and you can search for all of them independently, and you can know the algorithm behind, so you can know which one is used in which problem. And then we will have the maximum iteration. The maximum iterations here, like I can say to the model, so after 100 iteration, stop. 100 iteration mean 100 false, and so on, stop. The worm start we are not using yet. The verbose we are not using yet. The n underscore jobs we are also not using yet. Then we will have the classes. The classes, if we are entering an ND shape array, we enter a coefficient, the number of features, the number of classes, and so on. Then we will have the intercept. So again, the goal here, what I'm showing you, is the official documentation of the logistic regression parameters. We don't usually use all of these parameters inside our problem. We only use one problem, or not one. We use the needed attributes or needed things inside of it. So is there any question inside the logistic regression? Go on if there is any question. So now for the lab. The lab I have done it before, so it won't be that hard to write and explain on it. And again, I didn't do any optimization in it or training any optimization, since the optimization will do a very bad work inside of it, and it will take so long to make the optimization and so on. And the optimization here mean tuning. Tuning mean using different parameters to do different things, or even do something else. So let's continue till windsurf or the things load. So my question is, what is SVM? What do you know about the SVM? SVM stands for Support Vector Machine. So what do you know about it? Go on.
SVMs is an algorithm that works on separating the data by two margins. Those two margins will make the decision boundary in the midway between them, between two classes, and it elevates something known as the kernel trick, which is mathematically we're transposing the data into an infinite dimensional latent space to be able to separate among the different classes, and then we're bringing it back. It's a mathematical trick. This is the mathematical concept behind the SVMs, and as you've said before, it can be used either for classification or regression problems, but it's well known for classifications.
Yes, this was perfect. So let's continue. For an SVM. SVM stands for Support Vector Machine. It is also a supervised. Yeah.
The slides, it's not changing.
Yeah, I know. I'm just talking to you. Don't worry.
Oh.
And here I have switcher. So as he have said, Support Vector Machine stands for SVM. It is a supervised learning algorithm that used for classification and regression tasks. It tries to find the best boundary known as a hyperplane. A hyperplane, it is a line that separates the data points from each other. And our goal here is to maximize a margin between these points. So as the margin maximizes, the model knows that this is red and this is green. But as the margin collapses together, it won't know what is happening here. Okay. So our goal, it is useful when you have a binary classification like spam versus not spam, cat versus dog, or it can be used for multiple categories, and it will have multiple hyperplanes, but it will be transferred to another dimensions. The key concepts inside for a support vector machine is the hyperplane. The hyperplane here is the boundary, a decision boundary. The decision boundary is separating different classes inside our feature space. Our feature space here means the space that we are using or working with. Then we will have it represented by an equation of wx plus b equals 0. This is the main margin. Then we will have another margin that known as, we can say, wx plus b bigger than 0 for a positive class and wx minus b for a negative class. The support vectors. Do you know what is the support vectors? Why do we use a support vector? Look, for a support vector machine problem, we have something called support vectors. And support vectors here means the closest data points to a hyperplane or to the margin that we have. We have, you can say, 3 lines. The 3 lines, we have wx plus b equals 0, which is the main margin. Then we will have wx bigger than b, which is the positive margin, and wx plus b smaller than 0, which is the negative margin. The support vectors is the points that you can say it is located in on the lines, which is wx plus b bigger than 0 and smaller than 0. The ones that is located on the wx plus b bigger than 0, it is a support vector, positive support vector, and we can say that here the margin can be smaller. We cannot maximize the margin here because we have a point that supports this margin or this line. And same as for wx plus b minus 0 line. The margin, what is the margin? The margin here, I mean the distance between the hyperplane and the support vector. And our aim, again, is to maximize this margin as big as possible. Then we'll have a kernel. So what is a kernel here? I mean with a kernel here, it is a function that maps data to a higher dimensional space, usually using an SVM for a 2D class or a 2D categories classification. We use the normal space, 2D space. But if we have a multiple class category, we use the kernel. The kernel will transform our problem to a higher dimensions. And then we have something called hard margin and soft margin, and we will be talking about it soon. So is there any question inside the SVM now? And this is what I was talking about. A support vector is what is closest to this line and this line. And the goal here is to maximize the margin between the positive line, the positive margin, and the hyper and the negative hyperplane margin. So we can say that if I have squared dots, squared points, and the round points, and I have 3 sheets, and the 3 sheets here must be the margin. So the first sheet I put it is the main margin. where this I can say that it is the line that separates between the positives or the blue squares and the red squares. And then we will have two other margin, which is the positive hyperplane and the negative hyperplane. So where to put this? We put this when we have we put it on the first point that we see for a positive. We put it, which is the positive square blue blue square points. We put it here, so it will touch the first point that we can see. Then we have another point. This point we put this plane. We put it that touches the negative point. The hyperplane is used to separate the different classes that we have. Okay. Then we have the support vectors. Again, margin, it is the something that separates the two class points. There are many possible lines to separate them, but my goal is to have the margin that separates, that has the maximum margin, or the plane or the hyperplane that have the maximum margin. So we chooses the maximum distance between the closest points inside of each class. So do you have any question till now? If there is any question, go on. Okay. So let's continue for our SVM thing. We must again create a robust separation. So let's continue for our SVM. Then a mathematical computation of the SVM. Again, we have a positive margin here, which is Wx plus B is equal to A or bigger than A. Then we have the main margin here, which is Wx plus B is equal to 0. And we have the lost line, which is the negative hyperplane, which is Wx plus B is equal to minus A. Our goal, again, is to maximize the number, the margin between these two hyperplanes. And the support vectors here is this positive point and this positive point. Why it is called a support vector? Because it is the points that support the positive hyperplane. And here we have a 1 point. This 1 point is the point that supports the negative hyperplane. So I have a question. Do you think that we can remove these support vectors? What happens if we remove these support vectors? Go on, Manna.
Okay, as I have mentioned before, we have to think why we have the hyperplane or the decision boundary, and we have the margin. The margin is vertical, so I need this line to act like a separation or whenever. So
say again. Say what I said again, because I didn't hear you.
You say I'm saying you have mentioned two lines. The vertical and the horizontal line. The vertical line, or maybe the
vertical
hyperplane
and the
or the
horizontal
decision boundary.
Why would you use a vertical?
I mean, the margin.
This is the
vertical, the horizontal line.
Yeah. Can you have
the vectors
more stable internet?
No.
Else you have said, and then I can't hear you at all. So say what you have said again.
I can type in the chat. I can write.
I can't hear you at all. Yeah, you can write if you can write, Minnak, write to me in the chat and I will see it. Marwan, go on. Marwan Bak.
Okay, if we remove the support vectors, the boundary itself will be removed because it depends mainly on the support vectors.
Yes. Yes, you are right. Most probably, the points that is used for a support, I mean that the vector will be benefit for creating a margin. Yeah, it will be beneficial for creating the margins. But if I remove this point, these two positive points and the negative point, which is the support vector, here I can maximize the margin. I can maximize the margin to be at here and to be at here and here. So the margin is maximized. But the point here is while maximizing the margin, I don't want to lose any data points. I don't want to use any useful information. And most probably the support vector points is one of the most important points that the model relies on determining the space or the margin. We have W, and W is the normal vector to the hyperplane, which is mean the direction perpendicular. We take a point, the positive point, and the main margin or the main hyperplane. And we calculate the distance and put it inside the W. And same as for this, and same as for this point. So we can say W is the normal vector, which is determines the direction perpendicular to the margin that we have to calculate the distance. And BB is the offset or the bias. This is representing the distance of the hyperplane from the margin, which is the distance of this hyperplane from the margin, along with the normal vector W. And the bias is determined by a mathematical equation, and I would share it with you, but not now. I will send you a full documentation about the computation of how did we determine the W and how we determine the P. And the X is the feature that we have. Then we have the distance between a data point and the decision boundary. And it is calculated by WT xi plus b over the norm of the W. And I will share it with you again. How did we calculate this? Because I don't think it is a complex mathematical equations, but we use differentiation and integration inside of it. So it would be beneficial for you to see it and study it in person. Ahmed, go on. Ahmed.
I'm asking about the difference between di and the gamma. What is gamma in the drawing is the distance between the two support vectors.
The two
Is that the same
the
as
two
di?
hyperplanes, not
Okay,
the
the
two
two
support
hyperplanes.
vectors. It is yeah, which is I have said it is B. Gamma is the determination of the P. B is the offset or the bias terms representing the distance between the hyperplane of the origin and the normal vector. So the gamma is the maximum distance that we could have between the two hyperplanes, which is the positive hyperplane and the negative hyperplane. This is gamma, and it has an equation that I think it is 2a over norm the W. This is the equation that you use to tell the gamma. But for the I,
Then what is, okay,
the
yes, what is what for di?
I
What di? How could we represent di in
I will
this
tell you.
diagram?
Di is the distance between each point and the plane. So this is di1, and this is di2. di1, which is x1, di2 x2, di3 x3, di4 x4, di5 x5, and the d represents the distance, and the I represents the number of the point that we are using or the feature that we are using. So I here determines that if we have 11 features, what?
If we have what?
If we have 11
di
features,
determines, okay. Then we
yeah,
have
if we have
11
11
di.
features, we'll have 11 di and 11 xi.
Okay.
And now we are
Thank
going
you.
to talk about the C. You're welcome. The C. What is a say inside our SVM? We have something called the hard margin and the soft margin. The hard margin, it is something very, very, very strict and does not allow any points to be inside our margin. It maximizes the margin. It is very sensitive. It requires a perfectly linear separable data. The data must be perfectly separated, and if it's not, it will have very high penalties, and it will try to maximize the margin as possible, as it don't say that there is no data required to be inside this margin. Regularization here, it is not applicable. Complexity, it is a sample, and the computation is efficient, but you must make sure that the data will be perfectly separable. And how I would know this before entering the model, this will appear inside our visualization. The soft margin, it maximizes the margin, but minimize the margin violations. Hard margin does not allow any violation in the data, but for the soft margin, it allows. It says that it's okay to have 1 or 2 points inside our margin. It is robust, soft margin robust, handled noisy data with margin violations, controlled by something called the regularization parameter C, may require computational resources. So this is the difference between soft margin and hard margin. And the question here, what if our data is non-linear? If the data is non-linear, that means it cannot be separated by a line. So we use something called the kernel track. And we have talked about the kernel from a while. The kernel here means that we can separate the data in a higher dimension, 3D, 4D, 5D, according to our highly dimensional data. It creates a non-linear decision boundary. Common kernel, it is linear, polynomial, Gaussian, and RBF, which is the most commonly used. And you can search about them in detail. But the linear, it is what we are using. Polynomial, it makes the data makes the margin in a polynomial form or a parabola. RBF, which is a Gaussian, and so on. Training, how does training works inside the SVM? Training works, it is about minimizing. What? Minimizing this equation, which is half norm W squared plus C zeta R, summation of zeta R. This is the main equation that we are depending on minimizing. We use quadratic programming, SMO algorithms in practice, and it finds what? Our goal is to find the best weights that will fit our problem, the best boundary, the best margin, and because the data is convex, we must guarantee the global minimum for a gradient descent. Go on. Ahmed, go on.
Yeah, what is the I? What are
Again,
the what
it
are
is a
the Is?
coefficient. Yeah, it's a coefficient. The I
How
here,
is it
it is a
defined?
coefficient.
I mean, how is it defined?
I will tell you now. But is there any other problems inside the for any parameters of it, of the other things? Hello, can you hear me?
Yes.
Okay. For the zeta R, our goal again is to minimize. So we have something called weight, and we have called W, which is we have called it. We have the C, and we have known what is it. So the zeta or the xi, it is a slack variable. A slack variable measures the i's data points or the margin constraints, and it appears only in soft margin SVM. We have talking about the hard margin and soft margin. For a hard margin, it does not appear. We don't have something called zeta I, because hard margin does not allow any penalties or violations for the data. But for soft margin, it allows it. It calls a slack variable. A flag variables in real world data means class overlap. Some points are noisy or perfect separation is impossible. So we cannot use here any, you can say we cannot use here a hard margin. So the separation, linear or perfect separation will be used. So we put this parameter. So it says that we can have some noise or class overlap or impossible, or that the separation is impossible. So it appears only in soft margin. Okay. So if the point is correctly classified according to what we have, we said that the zeta is equal 0 or xi is equal 0. So this point is correctly classified and it is outside or on the margin. It can be a support vector or outside the margin and there is no violation. But case 2, if the zeta is between 0 and 1, it means that the point is correctly classified, but it has some violation that it is inside the margin, but it have a slight variation. But if the xi is bigger than 1, it is misclassifying or it is on the wrong side of the decision boundary. And again, it is usually used for what? It is usually used in soft margin. And the parameter of C zeta I, it is a penalized violation. Okay. Our input is a feature matrix. Features should be scaled, and again, the features should be scaled. The scale, you can use the maximum, minimum normalization or the we have two ways that we have talked before. You must scale our data with one of these methods. So again, for an SVM, the data or the features should be scaled before fitting to an SVM. Because SVM is very sensitive to a feature scale. And it is always a standard scale, always use a standard scaler. But for some problems, you can use minimum, maximum normalization. When to use an SVM, we use it for a small data set, a high dimensional data, a class separation, or something that needs a strong boundary. And for a hyperparameter tune, what do we tune if the model don't have the accuracy that we needed? We use the C, regularization strengths, and it is especially when we are using soft margin. Kernels. We use the kernels, and especially if we have a hyper or a high dimensional data. We use the gamma, smooth boundary for small gamma for or the gamma. This is control how far the informate of the points can be extended. Or we can use a small gamma for a smooth boundary, large gamma for a complex boundary, but again, a large gamma can be risked for an overfitting. How we tune it? We scale the feature, try the linear kernel. Then we can, if there is an underfitting, we can try the RBF. We can use the grid search or the cross validation, and I will talk about it at the end of the session if we have time. And then we tune C gamma and compare the validation scores. And I have provided again the link of our data or the link of our support vector machine documents, so you can use or you can see which data can be used when. So let's now return to our lab. Our lab will be 2 labs in one. The first lab will be on the on the logistic regression, and the second lab will be on the SVMs. So let's go. Is my screen appears to you now? Okay, I think it appears. Let's continue. First of all, here I didn't use any data set. I have imported data sets from sklearn, and I have used the iris, the famous iris data set. And then I used the pre-processing to do what? To normalize our data into standard scaler, so the model can fit it inside the sigmoid function correctly without needing anything. So first of all, what I have done here, I have loaded my iris dataset inside iris, and I have loaded the data. Load.iris, load underscore iris. I have said datasets dot load underscore iris. Then, yeah, go on.
That's good. Assignment, we can use a pre-processing, or we should do it manually.
You are saying pre-processing from sklearn?
Yes.
You can use it. If it's beneficial to you, you can use it.
Okay.
Okay. Then, again, when loading the iris dataset from datasets of sklearn, we are not loading the full dataset or the things that we have loaded before. We are here separating the data directly into the x.data and y.target. And here we can find that x have what? X have an array of the numbers that it is inside the data. We have seen it before, which is spatial length, spatial width, and the other two features that we have. And the iris dataset, it is a very, very small dataset. And for the y, we have a target variable, which is 0, 1, and 2. It is 3 categories. It is a multiple category data, which is 0, 1, and 2. And we have 3 different types of flowers. So I have determined the first type as 0, the second type as 1, and the third type as 2. And I didn't transform anything to anything. It is loaded from dataset.iris. But if I want to transform the categorical data into 0, 1, and 2, we can use something called one-hot encoding, and we have talked about it before. And then here we have scaled our data using a standard scaler, and we have saved it inside x_std. And here is our thing, or here is our data after scaling. So we can observe that after scaling our data, we have seen that the data is minus 9.006 power e of minus 1, power e of 0, and so on. So the scaling here is from 0 to 1. So be sure to know this. It is between 0 and 1. Then we have imported our logistic regression. So can anyone tell me what is multi-class OVR? Can anyone tell me what does this do? We have said that it is normally go on, Marcel.
One OVR is for one versus rest or one versus all.
Yeah.
It takes every classifier or each classifier and get its score. And it does the same for all classifiers in parallel. Then takes the
Yeah, that's perfect. Go on.
Then takes the argmax of the output scores.
Okay, that's perfect.
It takes the biggest
OVR.
one of them on.
So OVR means one versus all. When we have a multi-class category or a multi-class problem, we can use one versus all. So we take the first target versus all, the second target versus all, the third target versus all. So what is happening here? First of all, we create a logistic classifier object that is called a CLF, but we didn't train it or did anything yet. Then we have one versus rest or one versus all, which is a multi-class classification. Why do we need it? We have the binary classifier for a 0 and 1. But what if we have a 3 classes like here, A, B, and C, or 0, 1, and 2, and so on? One versus all means we take class A versus B plus C. Then we take B versus A and C. Then we take C versus A and B. And the classifier gives us a probability. And the class which with the highest probabilities, you can say it wins. Then we have the intuition. Instead of solving the data for A only, B only, and C only, and it will have some kind of a problem. No, we take our features and compare it to A, B, and C with one versus a rest. And the strongest probability that we have, it says that is a class A or a class B or a class C. Then we say that the random state is equal to 0. What is meant by a random state of equals 0? This controls the randomness or the shuffle inside the data. So same results every time we run the code. So this is for reproducibility, but logistic regression may randomly initializes the weight and shuffle during the optimization. So we don't need this shuffling. So I put it inside. I put it to 0. So when initializing the weight, every time it initializes the weight in the same order and do the shuffle in the same order. But we have something called multinomial. Multinomial means training a single model using a softmax. And softmax, it is more mathematically consistent, but in many problems we don't use it. And we use OVR for small data sets or a simple classification, and so on. But if it is more complex, we can use a softmax. So is there any problem here? Then here, we are trying to fit our model inside .fit so we can train our data. Here, we have trained our data by a .fit, which we have entered the scaled feature and the target variable. After we have said that the logistic regression we want is 1 versus the rest, and the random state is 0. Then I have entered you can say some kind of a small data or a small thing, and then we do the prediction inside of it. So it says an array is of 2 and so on. And I will send you a simple task for this notebook. Is there any questions inside of it, or anything is not obvious to you? And this is the very simple logistic regression. But if we have a very complex data set, and the task will be performing logistic SVM and neural network for the 2 data sets I have provided to you. So you will see that is more complex than this, but I need you to experiment it with your own and see what will happen. So is there any questions till now? And you can, at the end of the session, you will have my GitHub. So if you have any problem, you can enter my GitHub and see how it goes. Here for an SVM, we have loaded a dataset that called make moons. We have entered something called a pipeline, and I will explain it to you, and it's standard scalar. We have a polynomial feature and a linear SVC. First of all, here we have an X and Y from make moons. X is generating the instance, and Y it is the labels of X, or the answers, either 0 and 1 or 1. We have in samples of 500, we have a noise of 0.3 and the random state of 42. Then we try to visualize it, and this is how we find out. So can you tell me what do you find here from this observation, and how can I apply SVM on it? What do you observe from this visualization? Go on, Marwan. Marwan Bakr. Go on.
Okay, we can see that it's similar to the hyperbolic plane we saw before.
Okay. And what kind of margin that we can apply for this data? Kernel, okay, we can apply kernel or polynomial feature. Yeah, parabola, kernel. Because the data here, it appears to me, but let's see if you are applied kernel here, we can see that it is only 2 features. It has only 2 features inside of the data. So let's continue and see if we apply kernel or not. So then we have the X, which is the feature, and this is the array that our features will have. Okay. And here, so let's go back. So here, when the label y is 0, it represents by the blue squares, and if it is 1, it represents by the green triangles. And then we say that X is containing 2 features, which is X1 and X2. For X1 and X2, we have 2 target features, or 2 target variables, which is 0 and 1. So this is what appeared, and this is our 2 features inside X, which is X1 and X2, which is the 2 features that we are measuring the moons with. So if we have seen the first 5 values inside an X, this is what we have. 0.83 minus 0.2, 1.18 to 0.92, and so on. Then we have the Y, which is the target that we want to determine. So we find that the first one is 1, 0, 1, 0, 0. Then for the SVM, what we applied that it is a polynomial feature, which is a degree 10. A standard scalar, we have applied a standard scalar to scale the data. We have applied a loss of hinge. So what do you think this line do in detail? Okay, so let's make it more simple. The line here appears, it does something called a pipeline. So what is pipeline inside scalar? This is the first question. Ala said something before that it wants to use the pre-processing thing from scalar. So pipeline does what? Automatically applies a pre-processing steps before the training model. But this is used for, you can say, small features and small data set. So what does it do? It creates a polynomial features. It scales the data and trains SVM. The pipeline do it sequentially and safely. You don't need to do anything. So what we have from these 2 features, this transform your input features into X10 or a degree of 10. So from 2 features, we have now 10 features. Okay. So why did we do this? Because a linear classifier put a polynomial features allowed. Linear model to behave a non-linearly. So our goal here now, after scaling our feature or making our features multiple by 10, we use a linear model to behave non-linearly. So this is why it is just to trick the linear model of the SVM without using the kernel. Then we standard scalar our data with a mean of equal 0 and a standard deviation of equal 1. Because the SVM is again sensitive to feature scale. So if one feature is large like X power 10, it will dominate the training. So I don't need this to happen. So I use a standard scalar to do it. Then we have a linear SVC. C equal 1, this is the regularization parameter. Large C and small c to determine if you have a soft margin and a harder a small margin, or a soft margin, or a hard margin. Large C means stricter, less tolerance, no violations. Smaller c, more regulations. And the loss is equal to hinge. This is the standard deviation, SVM hinge loss. And it penalizes the points inside the margin, but it allows this violation. Okay. So the question here, why didn't we use the RBF kernel? This approach actually explicitly transforms the features, then applies a linear SVM. The difference here is that we do the polynomial feature explicit as then we do feature mapping, did a kernel trick in the A training, and that's it, without using an explicit RBF training. Then we fit our model, and then we have to predict this data, and we have the answer of it is a class of 0. And then here, we want to visualize how the data is, how the SVM is done. And this is how the SVM is done. You can see here that there is some penalties. The penalties comes from the blue points inside of the green triangles. But it is okay because I have used a soft margin to allow a regularization thing. So it won't make a violation, or it won't strictly do, because if I use a larger margin, it will be strictly used, and it can have an overfitting thing. So these points, we can say that we have classified an accuracy of, I think, 90 or 90% correctly, and this is just some violation inside the data, and it can be some noise actually, and you can remove it, but this is according to our data set, and this is the simpler of the SVM. Here we have applied an RBF kernel. Okay, we have applied it by importing the SVM import SVC, and we have applied a standard scaler with a kernel of RBF and a gamma of 5 and C equals 0.1. And again, smaller the C is, the more penalty that we will have. And this is what we have found out, or this is how the margin goes after doing an RBF kernel. You can see here it allows some violations. The space, the margin was bigger, but now it becomes like this. And your task here is to apply a nonlinear SVM like SVC or with an RBF kernel, and compare the results with the nonlinear SVC. So is there any problems or anything that you don't know or understand correctly? If there are any problems, you can ask. And the last thing I want to explain today is the neural networks. And I will go through it, and I will leave the lab to you. The neural network. What do you know about the neural network? Go on, Marwan.
Okay, it's a way of learning for the models. It's basically structured from layers and nodes, similar to the neural biological point of view, and also uses the functions we mentioned from them before, such as the softmax and the sigmoid.
Okay, thank you. Do anyone have any other ideas about neural networks? Go on, Marwan Muhammad.
It's another model which leverages the perceptron model by replacing the step function into using other activation functions like the ReLU or the sigmoid or the JALU or the TANH or whatever. There is a wide range of activation functions. Its main point of strength, is that it breaks down the nonlinearity into the data, and it discovers patterns within the data that were not discoverable before.
Okay, perfect. Thank you. And Ala says that having the outputs and classify the input using functions like sigmoid and so on, I guess. So let's dive deeper, Ala, and let's say if your opinion is right or not. So now we can see that a neural network is what? It is like our brain or the human body, which is a simple neuron, gives a signal to another neuron till it reaches your desired body parts of movement. If you are moving your leg, your hands, but take care that our body does not work like this. It is a stimulus thing that it works very fast, so we don't determine which neuron is activated and which is not. So the concept of neural networks come from the human brain, that it has an input layer, a hidden layers, and an output layer. The input layer here is what we have taken, or the order that we have, then it goes to our mind, processes it, very fast processing, and give a signal to our neurons inside our body to move our hands, to move our leg, and it takes a millisecond or nanoseconds or something like this to work. So this is the idea behind the neural network. The neural network have an input units where I fit the features to my model. Then I initialize the weight. I say this feature is more important than this feature. And then I say that this feature is not important at all. And this is the connection weights to another neuron. This neuron does what? Summing the function and uses an activation function, and we will be talking about this. Then we do our computation and so on till we have our output. So the basic knowledge or the basic units for a neural network: an input layer, a hidden layer, and an output layer. For a neural network, it is an artificial neural network. What happens here again? We have a dendrites, which is the connections between the neurons and each other, or the main signaling point, gives us a weight, or a signal moves here from weight 1 or weight 2 to the output. So how does this work? A neuron receives an input, determines the strength or the weight of the input, or determines how important is this to our data. Then calculates the total. The total comes from what? x1 multiplied by its weight plus x2 multiplied by its weight. Then it enters an activation function. An activation function can be a sigmoid function, it can be a relo, and it can be many activation functions, and I will be talking about it. The value ranges from 0 to 1, so if it's 1, it will go out. If it's 0, it won't go out. But if we are using a sigmoid function as an activation function here, it will be with a threshold 0.5. So what is below 0.5, it will become a 0, and what is above 0.5, it become a 1. So this comes from the total weights. So I don't calculate for each neuron or each input independently. No, I take the sum of it and apply it inside an activation function. And for a very big connection for each neuron after the input, it calculates the summation of the input that it have and do the activation function and enter another neuron till it reaches the output. If the total weight of the input is greater than or equal to the threshold value, then it will produce an output. If the total weight that we have, which is x1 multiplied by w2 and plus x2 multiplied by w2, the weight input will be less than the threshold, so there is no output will be produced. So this is a simple version. So is there any questions till now? And take care that the input layer does not calculate the activation function and the summation and so on. It is just an input layer to enter our features. We have many activation functions that determines if the output will come out or not. We have something called the identity. After finding the summation, the identity says that if it's X, go out. If it's 0, don't go out. or if it's a 0, go out, if it's X, go out, if it's 1, go out, and this is the identity. We have the binary step. The binary steps here have a threshold. So if X is bigger than or equal, our threshold will be equal to 1, which is the summation of the input values. And if it's 0 otherwise, which is smaller than the threshold that we have here, so then it's a 0. Then we have the sigmoid function that we have talked about earlier, which is 1 over 1 plus e power minus sigma x. We have a bipolar function, then we have the hyperbolic tangent, and each one of it have a different usage and a different values. The sigmoid function binary sigmoid function, it is between 0 and 1. Then we have the bipolar sigmoid function, and it is between -1 and 1. And then we have the tangent, hyperbolic tangent, which is between -1 and 1. And we have a Rayleigh function, which is between 0 and x, and so on. So the activation function is determined according to our problem. Deep learning and a neural network. Deep learning, it is a branch again of a machine learning that is used in artificial networks with multiple layers to learn from a complex data patterns. So we use it for complex data patterns, yes, because neurons, you can say, divide the problem into simpler patterns, so the model can determine the complex data patterns at the end. The neural networks, again, it is inspired by our human body, in enabling the powerful capabilities in the areas of the image recognition, language processing, and so on. We have a neural network structure, and we have talked about it, and we will talk about the forward propagation and the backward propagation. Then let's continue how neural network actually learn. Our neural network learns with two ways: a forward propagation and a backward propagation. What is a forward propagation and what is a backward propagation? Let's go on. First of all, our neural network makes a prediction. Then it calculates the loss function, or how wrong, or measure how wrong it is, measure how long the prediction is, and then adjusts the weights by reducing the error inside of it. For a forward propagation, it does what? It takes the input, does the processing inside the hidden layers, and gives the output. No learning happens here. It is just a normal prediction for a normal thing. Then we have our backward propagation. What does the backward propagation happens? After the output here comes, it is a prediction. So we take the prediction, we compare it. We compare it with the original output, or the desired output, or the answer that we have. And it says that there is a difference between the desired output and the predicted output with 0.5. So this 0.5 sends back to our neurons, and it goes back from the output to the input to adjust our weights. So the output to neurons, it was too high by 0.3. The hidden layer, the hidden neuron says, how much did I contribute to that 0.3? And then it is go to a back propagation way, which is go from the output to the input to adjust its weight. And we have something called a dropout. When the model is too complex, we don't allow all of the neurons to be adjusted at once. We adjust part of our neuron. So we go in each pass independently and adjust its weight, and make a feed forward the propagation again, and determine the prediction, comparison, the error, adjust the weights with a back with a back propagation to determine our error. Is there any questions here? Okay. Then we have two main things inside our neural networks, which is a convolutional neural network. A convolutional neural network, it is used usually for images. Instead for looking at a whole image at once, they scan a small region of the image. So if we have a very big image that can take a wall or something, so we determine to cut this image into smaller squares, and these squares inside the neurons, it's used to detect the edges, the textures, the shapes, the preserved spatial information, and so on, and then combine the image, all of the image again, to say it's a prediction about it. Then we have the RNN, which is the recurrent neural network. It is best for sequences, and it has a memory actually. It's used for text, time series, speech, and they remembers a previous information. The loss function here for a binary classification, we use a binary cross entropy. For a multiple class problem, we use a categorical cross entropy. For a regression, we use a mean square error. For our optimization training process, we use a back propagation plus a gradient descent. How does this happen? We make a forward pass without learning, without doing without doing anything to determine the prediction. After determining the prediction, we compute our loss with this equation, and this equation that can vary according to our loss function that we are using. And then we compute the gradients, back propagation, and so on, update the weights, and repeats. We have so many hyperparameters inside the neural networks. We have architecture, we have optimization, we have regularization. Early stopping means that we don't have to iterate as much as needed. We can stop at 100 iteration, 20, 30, and so on. Number of epochs, number of layers that we have, we can stop at a specific layer to see the output. The learning rate, which is determined how the model will be stable. Dropouts, which means that we won't use all of our neural network. We will use part of it only, the training, and the number of neurons per layer. And we have something called user type, which is SGD or Adam, and we will see it now. And let's go to lab 3. And I will explain a lab, and the other lab I will upload it to you, and you can see it if you need. For this problem, we have 2 datasets. The first dataset we will have is the MINUSET or the MINUSET, which is 9 by 9, I think, numbers or so on, from 0 to 9, or we have the breast cancer classification. And both are using NNNs, or neural networks. So before beginning in the last lab, do you have any questions? Yeah, Minna, give me 10 minutes and I will be done. Can you see my screen now? If you can see my screen, just make an emoji or something like this. Yes. Okay, perfect. Okay, for now, we are going to address our dataset, which is our MSc dataset. What do you know about the MSc dataset? I think you have heard about it before. Go on, Marcel.
As I can remember, it's a dataset of pictures of numbers.
Yes, it is a dataset of pictures of numbers. And it have multiple versions, actually. So MSc stands for Modified National Institute of Standard and Technology Dataset. MSc contains about 70,000 datasets, 60 for training and 10,000 for testing. The image that we have is a grayscale, and it is 28 by 28 pixels. Each image represents a handwritten digit from 0 to 9. So it has 10 classes, actually. And you can say the pixel values, it ranges from 0 to 225. It is flattened into a vector of 784 features. So we have a very number of features. So it is used for logistic regression, SVMs, neural network, and CNN, convolutional neural network. And it has many versions, actually. You can go and search about it. You will find many versions of it. And here I have loaded the mini dataset from Keras. Then after loading it, we used a model that is called sequential. We have used the dense because we have hidden layers, and we have random normal. Here, what I have done here is dividing up my data into X train and X sub, X train and Y train, and X test and Y test. And I have said it is equal miniset dot data load dot load underscore data. And again, if you don't use this method, you can use the full version of the miniset dataset by downloading it, pre-processes it, and uses it. Then I have reshaped our X-train data. I have reshaped it to what? I have reshaped it to 28 by 28 pixel because sometimes the data can be bigger or smaller in according. So this is to make sure that the data is what we need. Then I determine the X.shape. We find that we have 60,000 rows with 784 features. Okay. And then what did we have here? We have a weight initialization of random normal with the mean equal 1 and a standard deviation equal 1. Do you know what does this do? And why is the mean is equal 1 and the standard deviation is equal 1? Okay. So what does random normal do? This is the first question that we can ask. This is for initializing its weights, or initializing the weight that we have. Initializing a weight by a sample of random values from a normal Gaussian distribution, which is a mean is equal to 1 and the standard deviation is equal to 1. This is a Gaussian distribution to initialize our weights. Why do you need a random initialization? Because if we initialize all weights to 0, all neurons will have the same thing. So no symmetry breaking or something like this. And the network will fail to learn a meaningful pattern from the data. So we use a normal distribution with the mean is equal to 1 and the standard deviation is equal to 1, and it will be initialized randomly. Then we did what? We have entered the sequential, then we used a dense layer of 128 layers with a activation function sigmoid and the kernel initializer, which is W underscore initializer, which is the random weight that we have initialized, and an input dimension of 28 by 28. Then we have determined again, we added another 128 layer with the same ideas without the input dimensions. Lastly, we used a softmax activation to determine our last 10 layers determine the last 10 layers before the output comes. Then we compile the loss using a sparse category cross entropy. And again, we have the binary cross entropy, you have the multi-category cross entropy, and we have another ways. And we use an optimizer that called Adam and the matrices, which is accuracy. And we begin our trainings. We have 118 parameters, trainable parameters 118. Go on, Ala.
Can we use the squared error here or this only? And what other ways?
Again, say it again.
Yeah, I'm saying about can we use the squared error and what the other
squared
ways?
error?
Yeah.
Look, the squared error is used for regression, okay?
So we can't use.
So this is not a this is not a regression problem.
Yeah. So
this is a multi. Yeah, go on.
So what the other ways you were talking about?
we have mentioned in the slide, we have the binary cross entropy, but it is used for 2 categories only. And you have the multiple cross entropy, which is for multiple categories, but it won't be efficient for my data here. And there is way many ways for category cross entropies or cross entropies. You can know it from the documentation, but this is one of the most known cross entropy. We did what inside this code? We create a sequential model in Keras. Layers are stacked one after another: output layer of layer 1, input layer of layer 2, input layer of layer 3, and so on. Then we use a dense 128, which is a fully connected layer with 128 neurons. Each neuron here connects to all input features with a dimension of 28 by 28. Then we use an activation function of sigmoid, so the neurons will have an output value from 0 and 1. Then the W underscore initializer is for the initializing. Then we have layer 2, which is again 128 neurons connected to the second hidden layer. Okay. And an activation function, the same as a sigmoid. So here, the point for a softmax, which is convert the output into probabilities, all outputs sum to 1. This is why I used softmax. And the highest probability that we have predicted the class. So actually, we don't use for the last hidden layers, the last 10 hidden layers or something, or for the output layer, sigmoid function, because it wants to be efficient. We use something like a softmax. Then we compile a loss function with a close sparse category cross entropy Y, because it is a multiple class classification. Label and integers from 0 and 9, and it is not one hot encoded. But for the multi close entropy, it will be one hot encoded, which will be very complex to our data. Okay.
Okay, so how we actually determine how many layers we shall like put in the code or something. Like we use here three hidden layers. The one is sigmoid, and then the second is sigmoid, and then the last one is softmax. So how we actually define how many layers we should have?
Okay, for defining how many layers should we have, this is according to your problem 1, according to your features that you have. So you can say that for determining the number of a dense layer or how many layers should I have, this will be according to your data set. How big is your data set? How complex is your data set? Because first, the number of dense layer, it is the model capacity. It is how complex patterns it can be learned. Level of abstraction, the risk of overfitting. So if you increase the number of the dense layer, it will highly results in overfitting and the training difficulty. So we can start, you can say, from the start of from the problem type you have, you use a linearly separable data. So you use a zero hidden layer with a logistic regression and so on. Then then you determine if you need a hidden layer or not. For a moderate nonlinear data, which is one like a mindset, you use from 1 to 2 hidden layers, which is used for tabular data, miniset, or small data sets. Results for from 1 to 2 hidden layers. For complex data, which is like image, speech, NLP, and so on, we use +5 hidden layers, which is use CNN or RNN instead of a plain dance. Okay, so it is according to your problem. According to what problem do you have? And take care of having an overfitted model or an underfitted model, because the model underfitting cannot learn from the patterns because you take it so simple, or an overfitting, the model memorize each detail because you have over put a hidden layer. So the design, we don't calculate it. We start simple, train and check, training, checking the training accuracy, the validation, the testing accuracy, then try again by tuning our model. So there is no, you can say there is no a rule of thumb that we can do to determine the hidden layers that we have.
Yeah,
Okay.
Thank you.
You're welcome. And here is our output and the number of parameters. Then we fit our model inside our we fit our data inside our model, which is the NNN. We have 10 epochs, 10 trials, and the patch size is 128. And here is our data set with a loss of 4 in the beginning, and lastly a loss of 2.3 with an accuracy of 10%. And this is not this is not bad, but I will leave you the enhancement thing. So you can enhance your data according to what do you see inside this data. Okay, and take care of something that the accuracy can be very bad, but the model is having a very good output values. So the accuracy is, you can say, an indication, but it's not the end of our story. And the loss function is an indication, but it's not our end of our story. I worked on a model for a while, which is the accuracy was 70%, but the model was acting very fine. So it's okay to have a low input or a low accuracy for a model that works well. And this is a small comparison between the 3 models that we have used. And this is my LinkedIn, my GitHub, and my contact info. And that's it for today. And thank you all for listening. And I hope you have enjoyed our session today. And I hope to see you at the nearest time. And thank you so much.
I'm sorry to interrupt, but I have a question
Yeah.
from the last session.
Go on.
And yeah, for the previous assignment, do we have to do the 2 tasks or just 1 task for the Titanic data
Do
set?
one task and the other task just train your you can train on it for better performance later.
Yeah. Should I submit 1 task, right?
Yeah. You should submit 1 task.
Yeah, okay, thank you. And
You're
for
welcome.
this session, we have like 3 tasks, right?
Yeah, you have, it is a 3 simple tasks, I promise. It is just a task to make sure that you understand the logistic regression, the SVM, and the neural network. Just for an optimization, just for optimizing the training accuracy, optimizing the model itself, tuning the model, and so on. And it is a very simple data set, so it won't take you long. And the bigger assignment is applying these 3 models on your working data set that you have pre-processed.
Yeah, which one? The banking one or which? Or we should use,
If you have, yeah, go on.
yeah, or we should use your notebook, like the 3 notebooks, and I don't understand.
No,
like,
it's not the 3 notebooks. The 3 notebooks, it is just you can solve it, so you have a better understanding for each model independently. But for the bigger task, you will have to apply the 3 models that we have taken on your Titanic dataset or on the bank market if you have finished it, finished pre-processing it. So you can evaluate each model for your data and how did you clean it. You can evaluate the performance of each model and compare each model and tell me at the end of the notebook which model works the best for the problem that you have.
okay, so we have like 3 tasks, which is smaller, and the big task actually working on the Titanic or the banking, right? This is what
Yeah.
what I'm.
Yeah.
Yeah. Okay. Thank you.
You're welcome. See you next time, and I hope you have enjoyed our session, and thank you so much. Bye.
Yeah. Bye.